In the previous video on this project, I was able to finish the backplane and implement all of the cards necessary to run something more complex, like calculating the Fibonacci sequence. And I was able to enter, modify, and execute that program using these functions on the front panel. But behind the scenes, those functions are still being driven by this prototyped hardware microcode. And now that I've completed extensive manual and automated testing on this prototype design, it's time to reverse engineer this into something like this. I'll start things off right by disconnecting the power supply to avoid any mishaps, and then remove the ribbon cable that connects the ALU logic card, the adder card, and the B and C registers. Next, I'll get rid of the positive and ground leads that are providing power for the clock, and then disconnect the reset, halt, and clock lines from the system bus, as well as the switch leads from the front panel. And I'll just shift things over here a bit so that I can get some better camera angles for the next part to tackle, which are these two prototype boards for the data and address gating. These are double pole relays, so each relay can gate 2 bits. And because this was a prototype, I only gated the first 8 bits of the address bus, as I felt that this was enough for testing purposes. With those address lines removed, I'll move on to disconnecting these lines that provided some inline resistors for the front panel LEDs. Next, I'll disconnect the output from the program counter that displays the current address on the front panel LEDs. Then it's on to removing the connections for both the instruction register and the address gating from the system bus. And the last piece for these gating prototypes is to remove the 2 gating activation lines. And now it's time to move on to these control lines, which are really the heart of what the front panel functions are activating. And since I was basically building this on the fly without a schematic, I'm going to take some time to carefully label each control line so that I can trace it later on. With the relay computer now fully disconnected from the prototype board, it's on to disconnecting all of the front panel switches from the board as well. And with everything disconnected, I can now pull away the front panel assembly. I'm going to use my pizza paddle maneuver to carefully move the prototype over to my workstation. This is the first time I've ever transformed a prototype this large or complex to a schematic, so I'll definitely need to get some coffee and some good tunes for this next part. I'm going to work this board from left to right, starting with this 6-step sequencer that is used to run the microcode. And this circuit is really just a ring counter that has these integrated capacitors to control the speed of each step, and then some LEDs just to show which step is active. Then there are these 2 relays, which are the latch gate that keeps the function latched once the switch is toggled, and then the relay that helps shape the D-pulse using a combination of sequencer steps. Next, there are these two columns of relays that are used to create a small delay in the B and D pulses, which are needed to fine-tune the timing when activating the control lines. And now we get to the examine, deposit, examine next, and deposit next microcode. Each of these functions is gating the pulses generated in the previous sections to activate the required control signals through these many diodes that are buried under these many wires. So rather than pulling everything apart, I built this simple display to show which control lines are activated for each function, which really helped ensure that I was capturing the diodes on the schematic accurately. The final piece of the prototype to capture is the gating circuits, and while the data gating is more straightforward, the address gating needs a more philosophical moment. So I've been thinking about this address gating and the fact that right now it's 8 bits. It's been 8 bits for a while, ever since I built this prototype mock-up of the front panel. And I've come to this conclusion that I think that 8 bits is sufficient because that does give us the ability to address the first 256 bytes of memory, which I think in relay computer terms is actually good enough. I mean, if I need anything more than that, I can always use a tape program loader or the Arduino to load the program directly into memory. But frankly, I can't imagine loading a even 256 byte program using toggle switches. That would be quite arduous. I think my fingers would probably fall off at that point. Now that the schematics are done and the decision has been made about the address gating, it's time to create the physical layout of the PC board. While the relays and their respective diodes are a familiar sight, this board has some new capacitors and resistors to add to the mix. And since this board has only 32 relays, I can use that extra space to group the relays based on their purpose. And I'm also doing the same with the diodes, which should help in troubleshooting if any of those diodes go south later on. The final part in the design is the silkscreen layer, which captures any of the text or cool logos that I want to have printed on the PCB. I typically do a 2D view that shows the board without the green masking, which makes it pretty easy to see if there are any obvious problems with the spacing between the traces or the components. And once that's done, it's time for one of my favorite moments by generating the Gerbers and then sending them off to PCBWaaaaaaaay. It's hard to believe that it's been about a year since I first started working with PCBWaaaaaay. And over that time, I've sent them a lot of different designs, and they've been fantastic to work with. Many of the boards in this relay computer have now been manufactured by PCBWaaaaaay, and every single one of them has worked perfectly. And this Christmas, the team at PCBWaaaaaay surprised me with this awesome gift package. So a huge thank you to Elaine and Zoe at PCBWaaaaaay for all of your support over the past year. And now it's time to check out my other Christmas gift, and I'm thankful that it arrived safe and sound thanks to PCBWaaaaaay's use of extra foam and a protective vacuum seal with integrated bubble wrap on the boards themselves. And all of this means that your boards will be fresh, clean, and ready to go, and that's what it's all about. So check out PCBWaaaaaay for your PC boards, 3D printing, and even injection molding needs. They truly make your projects come to life. Now that the card is completed, it's time to interface it to the front panel, which was originally set up to plug into the prototype breadboard. Now, there will be a more permanent solution later on, but for now, I'm thinking I can just plug these leads directly into the IDC connectors. And for this exercise, I'll start by cutting the lengths of ribbon cable that I'll need, align the IDC connector, and then crimp it down using this handy tool. And with that, I now have one 16-pin and two 20-pin cables ready to go. Now, this relay computer is getting heavy, so I'm using some plywood as support when moving it, just to avoid flexing the backplane. And with that in place, I can install the new card on the far left so that we have some visibility, and then introduce it to its very messy counterpart. And since the program counter needs to connect directly to the new card, I'm going to remove the program counter and move it closer. And once that's done, I can connect these two cards and then plug in our two new 20-pin ribbon cables, which we will painstakingly connect to the front panel for the instruction, address, and all of the switches. And now that it's all hooked up, let's kick the tires. When I run code like the Fibonacci sequence, I don't really have any way to see the result on the front panel yet because the value is stored in the A register that can be seen way at the back. So I'm going to modify the A register to output the result and then install some LEDs along here just so we can more easily see the results. Well, the new card is working flawlessly, and I'm not so much amazed as relieved because all of those nights of translating that organically grown prototype board to this PC board has really paid off, and there's not a bodge wire in sight. So I'm really, really happy with the outcome on this card. And that takes me to the next logical thing to work on, which is this rat's nest in behind the front panel. It's just temporary while I'm designing the front panel layout, but once that's all done, there will be a PC board behind the front panel plate that would support the switches and the LEDs. And then on my to-do list, which seems to be growing and not shrinking, but I'm okay with that, I have the clock that has to be worked on. It's pretty straightforward. There's just 4 relays and a couple of capacitors, so that should be easy enough to translate into something somewhere. And then I have to figure out what kind of internal power supply I'm going to be using in the case. And I'll leave off with this announcement that I've decided to become an exhibitor at the VCF Montreal on January 24th and 25th. So yeah, I have no clue what I'm doing in terms of being an exhibitor, but I'm really, really looking forward to meeting as many people that are interested in vintage computing. I had a lot of fun at the Midwest last year, so I'm thinking it's going to be more of the same goodness. So hopefully you can make it out there. I'm going to be bringing along the relay computer, probably the teletype machine as well. And since the theme is Canadian computing, I'm just going to slap a Made in Canada sticker on this machine and call it a day. So with that, thank you so much for watching, and I'll see you next time.